Greetings. Welcome back to Paleozoic PCs, where ancient computers still walk the earth. So today on Paleozoic PCs, I'm going to open with a little idea for a segment I have featuring Professor Pterodactyl, who's a boring old bird that likes to give excessively wordy dissertations about obscure technical subjects related to old computers. So, as you might guess, based on the last video, today's lecture is a brief rundown of Tandy 1000 memory architecture. Basically, this is a quick breakdown of why the Tandy 1000 differs and is unique from both the original IBM PC and the IBM PC Jr, its two major inspirations. So I'm going to try to run through these slides and not be too blabby about it. And if there's anything you miss, by all means, feel free to pause the video if anything looks interesting. So, moving on. Our first slide is about the standard IBM PC Memory Map. So, in brief, if you already know this, go ahead and skip ahead, but in short, your standard real mode IBM PC, which has a total, the CPU, the 8088, has a total memory space of up to 1 megabyte of RAM. That is 5 hexadecimal digits. So how is it broken down? Well, you probably know. The bottom 640K is dedicated to RAM. Then following that is an area that's dedicated to video memory. And above that is where devices and ROMs live. So as the slide lays out, the bottom 640K starts from hexadecimal 0. It works up to 640K. DOS requires all memory in that area to be contiguous. It should start at 0, end at 640K. There's a little marker it maintains, which is the end of memory. And when you add memory to a system, let's say you have a 256K PC, it's easy to know where it goes. It simply starts at the next address after that. And also, to emphasize, video RAM is separate. It lives by itself, this little hole, upper memory. It's not part of base memory. It's its own entity. Easy peasy. So, IBM PC Jr. Now, when the IBM came out with the Jr, they essentially fused a home computer like an Apple II with the IBM PC architecture. So, in the IBM PC Jr, all the memory that's in the machine, it's wired into the base unit, 128K in your standard enhanced PC Jr, that is all shared between the CPU and the circuitry that generates the output for the CRT. As the slide lays out, DOS starts at 0, just like it does in a normal PC. And at the top of memory, a minimum of 16K of RAM is set aside to do text and graphics in. Now, the same 16K is also mirrored at address B800, which is where the CGA memory in a standard PC resides. And that is how the IBM PC Jr manages to be compatible with PC software that writes directly to the CGA memory. So, again, the entire 128K in the PC Jr is accessible to the CRT register, and it can actually use multiple pages. Now, the important thing to remember, again, is DOS expects all memory above it to the end to be contiguous. So how this works in the Junior is, DOS is at 0, it ends somewhere around the 30K mark. That goes up and it stops at, say, 112K because of the minimum 16K stolen off the end. That's great. That works fine for 128K PC Junior. But of course, 128K doesn't go a whole lot of distance. Even didn't go that far back in 1984. So what happens when you add IBM RAM to an IBM PC Jr? Well, I think the title of this slide gives it all away. So the Junior works just like the big PC, in that when you add more RAM to it, it starts above the RAM that's already in it. So if you got 128K PC Jr. and you add 128K to it, starts at the 120K mark and ends at the 256K mark. Add another memory card, another sidecar. You have to flip the switches on the back, so it starts at 256K, so on and so forth. The problem with this is video memory still has to come out of the base 128K. And remember how DOS doesn't like holes. So this means that from a certain point of view, an expanded IBM PC Jr. is actually fundamentally incompatible with normal DOS memory management. As this slide lays out, essentially the way they work around that is that you have to load a device driver on an expanded IBM PC Jr. and you have to use these various tricks to essentially make DOS swallow the screen memory and run all your programs afterwards. And that wastes a substantial amount of memory on one hand, and on the other, it creates incompatibilities with existing PC Jr. software, because unless you dedicate the entire bottom 128K to being set aside for screen buffers, when it tries to create a screen buffer, it might not be where it expects it to be. So it was not an ideal solution. So what did Tandy do? So on a basic level, the video system in the Tandy 1000 is compatible with the IBM PC Jr. with one exception, and that is when you add additional memory to a Tandy 1000, you don't put it after the original 128K. You put it before the original 128K. At startup, none of the memory inside of your unexpanded Tandy 1000 is actually in the normal DOS area. It actually all lives up in the video area. And so when the BIOS starts executing, it does a simple RAM test, counts fingers and toes up there. The next thing it does is actually look and see if you have an expansion card with a DMA chip, and if it does, it initializes the DMA chip because it assumes it would need that running for expansion memory to work. And then after that, it starts looking for expansion memory. So it starts at 0, writes a byte, reads a byte, gets the same thing back. It moves up to the 120K mark, checks. 256K, checks. Again, at 128K intervals. And once it's determined how much external memory you have, it writes a little register on the big blue video controller that then moves the video controller memory to the end of the expansion memory. So however much memory is natively in your Tandy 1000 wired behind the video chip, that moves to the end. So this is the first important takeaway of this video. If you are going to be creating your own Tandy 1000 memory card, or if you're going to be configuring something like one of those low-tech 1 meg cards to go on your Tandy 1000, do not configure it the same way as you would for an IBM PC with the same amount of memory. So if you had a PC with 128K on the motherboard, and you wanted to put one of those cards in and fill it up to 640K, you would map 512K starting from the 128K boundary and end it at the 640K boundary. That is not what you do with your Tandy 1000. With your Tandy 1000, you start at 0, you go up to 512K, and then let Big Blue fill up the rest. Now, moving on from there. Let's talk a little more about that moving behavior. So this table is from the Tandy 1000 TX manual. Tandy 1000 TX was the last model that used the original Big Blue memory chip, and it also happens to have the most complete table of the capabilities of that chip. So that is why I'm displaying it here. So I've been doing some experimenting with my expanded 1000EX to determine if configurations other than those documented in the EX manual for this specific configuration of Big Blue are valid. And spoiler alert, my experimentation suggests not. So I'm just going to touch really quickly on these bullet points. So there are two kinds of Big Blue. The ones in all Tandy 1000 models other than the EX and the HX have 128K wired up behind them. Only the EX and HX have 256K. So if you look at this table, the way you interpret it is there are 3 bits on this memory register, which lives at A0 hex. So those are basically address bits, just like you were decoding the top 3 address lines, A19, A18, A17. What those translate to is that is the starting address of the top 128K of RAM that's on your Big Blue. I say top because the other 128K on those 2 models that have 256K, it is actually lives 1 page below it. So basically it's the center of the RAM behind your Big Blue. And that is why if you look at the chart, you'll see this interesting thing that the Big Blue with 256K uses the same jumper configuration, the same register configurations as a standard 128K 1000 would if it had 128K more expansion memory. So, so far as I can tell, these charts are complete. Now, you'll notice that there are actually, for both the 128K and the 256K variants, there are actually 2 undocumented combinations. Because you'll see at the bottom of each one where it's all ones. That is the mode that the Tandy TX apparently uses. So I did some checking to see if the other modes do anything else, and the answer is they don't. So basically any configuration that sets Big Blue over 512K puts it in Tandy TX mode. Tandy TX mode, that tells Big Blue to no longer backfill base memory. Instead, Big Blue just starts acting like it's a video card. It just lives up in the video address area. It doesn't try to fill anything up. So, why am I talking about this? As I said, one of the confusing things you'll find when you look at the tech manuals is as you go through the models, basically whenever they added a model, they would add additional lines to the table they had for configuring that register. Not all of them are valid for every machine. The BIOS in every machine does not test for every possible combinations. So, for instance, even though this is hearsay, I do believe it is correct because based on some posts I've read on the Vintage Computer Forum and others, that, for instance, if you put 640K of base memory in an original Tandy 1000, it will not test for it and then configure itself like the Tandy TX configures it. It will still try to steal memory. It'll still try to backfill, and thus it'll still have 16K less than 640K, etc. So again, why am I talking about this? So one of the things that we discovered in experimenting with some of the pre-work we did on creating my memory card was we could apparently successfully expand a Tandy 1000 HX or EX by simply taking a 512K RAM chip and using it with 0 decoding, essentially using A19 as the chip select. And it appears to work. Now, the concern that I am going to point out here is we were not able to determine definitively if this is a conflicting configuration or not. Your gut feeling would be that, oh, if you have a RAM chip in there and it's clashing with the built-in memory, it would like crash the machine or something. So this has bothered me enough that I have created some basic programs, and I did some experimentation to try to see, with my RAM expansion installed in my Tandy 1000EX, what would happen if I were to intentionally put the big blue memory and expansion memory at the same location. And I'm going to show you a video of one of those explorations after this slide. But the short version is it appears that there is actually no valid configuration for a 512K memory expansion in a Tandy 1000EX without, that doesn't cause clashing, unless the BIOS in those machines is actually disabling 128K of the built-in RAM. Unfortunately, it is not possible to read this register. So I guess you could argue the only way to definitively prove that it's clashing would be to create a special memory card that you could like flip that page of memory on and off. But what my experimentations did reveal is that you can actually have those two those two memory sources mapped at the same address, and this does not immediately kill the computer with bus contention. It seems like they will actually run in sync and appear to work. Now, as Professor Pterodactyl is pointing out there, having two TTL chips driving the same input at the same time and trying to overload each other's outputs at the same time is not a valid configuration and could actually damage these chips in time. So again, the reason I'm pointing this out is if you decide to build your own Tandy 1000 memory card, I would strongly suggest you decode the bottom 384K instead of just wiring up that one chip. The one chip is really cool, but you can add a single, say 7400, and decode 384K and eliminate any worry that you might be slowly damaging your 1000. The link that is on this slide is a little emulator of the 7400 decode solution that I created in Circuitverse. It shows how it works. Feel free to steal it. Let's all play it safe out there with our Tandys. So I'm going to go ahead and roll the video now. This is a quick little demo of a trivial basic program I wrote that pokes values into the register which controls where the big blue memory is mapped, and does some writes and some reads, demonstrates that you can actually stack the internal memory on top of your expansion memory and not necessarily crash the machine. So I'll just go ahead and run this and I'll explain what it does. All right, well that was quick and unimpressive, but let me give you a quick walkthrough of what it did. You probably noticed the first thing that you saw happen was this colored bar appeared up here, that purple bar. That appeared up here because the program initially changed the segment register to the beginning of where video RAM is located when you have it in the 640K position, which is this area 9C000 that's the page that's aliased up to B800, the CGA area. So first thing it did is set it there, and it poked it full of this, which is hex 55. The next thing it did is it set the segment register to 5C, which is 16K below the 384 K mark. And you see it poked hex AA in there. Now 55 and AA are important numbers because these are both alternating bit patterns and they're the complement of each other. So in this one, this would be binary. I'm going to just do the 5, just one half of it. This is binary 0, 1, 0, 1. A, on the other hand, is binary 1, 0, 1, 0. So you see it read back from here and it got what it poked in there, which is a bunch of A's. So here, switching Big Blue to 384K RAM mode. What I actually did there is I took the RAM that was from the top of the 384K mark all the way up to the 640K mark, and I just moved it down 256K, which means it is sitting on top of the last 256K of my expansion memory. Now look what happens when I read back from this 16K under the 384K mark. I got all F's. It added these two together, gave me all F's. Now, then I poked it back in. So I said, okay, got F's, poked it back in. That's when this bar changed color. So you see how this is bright white flashing on top of this gray background? That alternating pattern, that's the attribute memory in the video RAM. That combination produces this attribute set. So then the next thing I did after doing that, so you saw it changed color. So I was able to write to that memory and it stuck and it worked. It didn't crash the machine when I wrote it back, nor did it crash it when I read it. It added it together. So then I changed the segment register back to B800 this time, not 9C, because remember the RAM's not there anymore. I actually went up to where it's aliased. The Big Blue memory is aliased into the CGA section. And then I poked A through Z into the character cells, which means I skipped every other cell. I skipped the attribute cells and only poked the character cells with this. And that's why the alphabet appeared up here. Now, here, I switched Big Blue back to 640K, which means I moved it back up. It's no longer overlapping. I switched it back to 5C again. Remember, that's where I initially poked A's, and then I overwrote that with F's. And now look, when I read this back, 255, 255, blah, 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 blah. That, and again, I'm just reading the character positions. You notice I am still getting 255s, which is the FF. I am not getting the characters I wrote when I wrote to B800. So that demonstrates a number of things. One, the machine will not necessarily crash when you put the memory on top of each other. It will read and write. Two, this is scary. Both RAM banks are driving the bus when I read it. That has a potential to damage things over the long term. And third, again, when I switched it back, the writes, when I went here, the writes when I went to the overlapping area went to both pieces of memory, because this is the Big Blue memory that's actually displaying this, but it's also went to the expansion memory. But I also showed that, and this is just for my own amusement, if I go to B800 instead, that shows that the thing that aliases the Big Blue memory up into CGA, it doesn't activate the bus. It just goes to Big Blue memory when that alias happens. So the contents that I wrote here were not overwritten by going directly there. So yeah, that's my demonstration that overlapping your SRAM with the Big Blue RAM is possible, very possibly without crashing the machine. Okay, we're back. So this slide that I have here on the screen, this is just a quickie because it came up in a question. I did actually try to clarify it with a comment, but I'm just going to run through this real quick. The thing that I didn't really clearly explain in my DMA spiel in the last video was, well, if you need DMA to refresh the expansion memory, why don't you need it for the base memory? And the short version of it is, is that because the video system inside the Tandy 1000, or the IBM PC Jr, is constantly reading from memory, that refreshes it. It's really that simple. The reason that system can't refresh the external memory is because the chip inside the Tandy 1000 is directly wired to the internal memory, and it can only read from that memory. It can't reach out and refresh the other memory. So that's it in a nutshell. Like I said, I did have some text explanations for it, but in case you were left wondering, that's what that's about. All right, takeaways from this video. Well, long story short, your Tandy 1000 is an amazing machine. It's a far better thought out computer than the IBM PC Jr was in a lot of respects. It's the machine that it should have been. So good job with that, Tandy. However, for all the good that comes from the Tandy 1000 being the spectacular machine it is, this does mean that these differences create some problems if you want to use memory cards that were designed for the original IBM PC. Not really a big deal. It just means that if you are going to make your own memory card for your PC, for your Tandy 1000, or if you're going to use a generic card like the aforementioned low-tech, you need to configure it properly. You need to remember the one big takeaway for the Tandy 1000 add-on memory always starts at the bottom. And the final takeaway is, if you're designing your own memory card, design it properly. Make sure it does not conflict with the possible positions of Big Blue in your... The point of my experimentation with those basic programs was just to demonstrate that it might not be intuitively obvious if you created a mistake. I would suggest only using configurations for expanding base memory that are documented in the fine documentation, unless you want to put in the work to prove that there are in fact undocumented states that will accommodate what you've come up with if you decide to put 512K or 640K starting at 0 in your EX. So thank you for watching this slightly unconventional video. If this is something you would like to see more of, in-depth tech dives into obscure old subjects like this, go ahead and let me know. If you never want to see anything like it again, try to be kind, and thank you for watching. My next video will be more conventional, with me showing off some toys that I've gotten to help me do testing of my memory boards on that 1000EX motherboard that I showed in the last video. So thank you for watching.